3.2, now we're going to be looking at the derivative as a function. Remember in the previous section, this x right here was not an x, it was an x sub naught, which took the place of a number. Instead of actually finding the derivative at a specific number, what we can do is find the derivative as a function of x. Instead of finding s prime of 4, we'll be able to find s prime of t, just leaving this a variable. So that's the only difference here, is you leave the x's in instead of plugging in numbers in place of x. Not that bad. Once again, the derivative comes from this secant line here. Here's an alternate form for the slope of a secant line. Here, this is the form that you use, instead of looking at the limit as h approaches 0 of this, you would be looking at the limit as z approaches x. The books that I've used in the past said it's the limit as a approaches b of f of b minus f of a over b minus a. I don't care which definition you use. If you've gotten comfortable with this one and you want to just stick with that, that's fine. If you think that this one might involve less arithmetic, I don't care, whatever makes you happy. Because in a couple of sections, we're going to learn some shortcut rules and get away from the limits altogether. Can't wait for that day, huh? All right, so this is the alternate form of a derivative. It is just that. It's an alternate. Okay, if you want to use it, great. If not, that's okay too. In example 1, we're asked to find ds dt. Remember, that's the derivative of the function s with respect to t. Do you want to try one using the alternate form just to see what it feels like, or do you want to stick with the h definition? Stick with what you know? Okay, we'll stick with what you know. So we're gonna pretend we don't have the alternate form because it's just piled higher and deeper at this point. And so we're going to find then the derivative by saying that ds dt, the derivative of s with respect to t, is going to be equal to the limit as h approaches 0 of s of t plus h minus s of t all over h. So this is going to be then the limit as h approaches 0 of t plus h over 3 times t plus h plus 1 minus t over 3t plus 1, all divided by h. Yeah. Okay, we can do this though. There's fractions here. In order to combine fractions, we have to get what? Common denominator. But before we do that, I'm going to distribute this 3 and see if I can make things look a little nicer. So this is going to be then the limit as h approaches 0 of t plus h over 3t plus 3h plus 1 minus t over 3t plus 1 divided by h. It would be nice to combine these terms, these fractions in the numerator, wouldn't it? In order to do that, we need a common denominator. The easiest way to get a common denominator is to multiply the two denominators together, isn't it? So we're going to say that our common denominator is going to be 3t plus 1 times 3t plus 3h plus 1. And what you multiply the denominator by, you also have to multiply the numerator by. And this one gets multiplied by 3t plus 1. So there's 3t plus 1 over 3t plus 1. So this is going to be equal to, we have the limit as h approaches 0 of 3t plus 1 times t plus h over 3t plus 1 times 3t plus 3h plus 1 minus t times 3t plus 3h plus 1 over 3t plus 1 times 3t plus 3h plus 1 all over h. Oh, yes, sir.
So you cancel out the 3t plus 1?
I stuck, you mean right here?
Yeah.
I stuck it in there so that I could have a common denominator. I'm now going to FOIL this out and distribute a negative t, because look, I can make this a positive plus and then put the negative in front of the t. And then what I'm going to end up doing is I'm going to distribute the t to these terms, the negative t, and I'm going to FOIL these terms out right here. And they're over a common denominator, so I'll be able to combine the numerators over that common denominator. At this point, it's like having a over b plus c over b, and then I'm going to combine that into a plus c all over my common denominator. I know that these factors are going to cancel because I multiplied them in there to force it to look like I want so that I can combine the numerators. I'm trying to get one rational expression on top. Okay, so this is going to be the limit as h approaches 0 of, when I FOIL this out, I'm going to get 3t squared from my first terms. When you right there, when you multiply the outside terms together, you get plus 3th. Inside gives us plus t. Last gives us plus h. There we go. This is all from the first term. Plus, now I'm going to distribute that negative t across here. So that's going to be minus 3t squared minus 3th minus t all over our common denominator, which is 3t plus 1 times 3t plus 3h plus 1. And this h over 1, can't I flip and multiply and put that right here in the denominator? Are y'all okay with that? I took this h right here that's in the denominator. Let me make another note of the rule that I'm using. I'm doing this. If I've got a over b divided by c over d, that's going to be equivalent to a over b times, that's a d, d over c. So I said, well, this is h over 1. So when I flip and multiply by the fraction on top, it throws that h into the denominator. This is just a reminder of the rule. I'm going to erase it so it makes sense later on when you look at the notes. All right, do we have things that are going to start canceling out? We have a 3t squared minus a 3t squared. You know, we have a plus t and a minus t. I think that's it. Oh, it does, doesn't it? Yeah. Okay, cool. Those cancel out too. So all we're left with on top then is a h, right? Well, isn't that going to cancel with this h down here? So we're left with what on top? 1. So this is going to be equal to the limit as h approaches 0 of 1 over 3t plus 1 times 3t plus 3h plus 1, which when we let h go to 0 is going to give us 1 over 3t plus 1 squared. That's the final answer. What we were asked to find, remember, was the derivative as a function of t. There it is. ds dt is equal to this. Ta-da! Okay, example 2. Differentiate the function, then find an equation of the tangent line at the indicated point. So we're going to take the derivative of this function. Y prime is equal to f prime of x, just using the notation. And that's going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This, by the way, is going to give us the slope of the tangent line, which we need to write the equation of the tangent line. Here's the point, and this is going to give us the slope. All right, so moving along. This is going to be the limit as h approaches 0 of 2 plus the square root of 9 minus x minus h, because you got to distribute that negative, minus 2 plus the square root of 9 minus x all over h. Distribute the negative, and we end up with the limit as h approaches 0 of 2 plus the square root of 9 minus x minus h minus 2 minus the square root of 9 minus x all over h. Do we have like terms that'll cancel out? Just the 2 and the negative 2, right? So that's going to leave us the limit as h approaches 0 of the square root of 9 minus x minus h minus the square root of 9 minus x all over h. By direct substitution at this point, we get 0 over 0, right? That's an indeterminate form. How are we going to evaluate this limit? We're going to rationalize the numerator by multiplying both the top and the bottom by the conjugate pair. We're going to take this numerator and we're going to multiply it by what? The square root of 9 minus x minus h plus square root of, and then we multiply the denominator by the same thing, square root of 9 minus x minus h plus the square root of 9 minus x. And thanks to our ability in algebra, this is not a problem to FOIL out the numerator. We end up with the limit as h approaches 0 of 9 minus x minus h minus 9 minus x all over h times that whole conjugate pair. 9 minus x minus h plus the square root of 9 minus x. Alright, what do I need to do now? Distribute the negative. So that's going to give us, I think I can continue along over here, the limit as h approaches 0 of 9 minus x minus h minus 9 plus x all over h times the square root of 9 minus x minus h plus the square root of 9 minus x. Anything going to cancel out? The 9's are gone, the x's are gone, which leaves behind just a h, or a negative h. Well, that h is going to cancel with that h, and when we use direct substitution here, we get negative 1 over 2 square roots, because that's going to be the same, of 9 minus x. So this is the derivative as a function of x. The instructions here, though, said to write an equation of a tangent line. To get an equation of a tangent line, we need two things. We need a point and we need a slope. So what is our point going to be? You don't remember, it's up there. 8,3. Equation of tangent line at the point 8,3. So there's our point. Our slope is going to be equal to f prime of 8. So that's going to be negative 1 over 2 square roots of 9 minus 8, which is going to be negative 1/2. Now we write an equation of a line. We can do that using y equals mx plus b. What are we going to use for y? 3 equals negative 1/2 times 8 plus b. So 3 is equal to negative 4 plus b. Add 4 to both sides. B is equal to, so what's the equation of our tangent line? Negative 1/2 x. That's the equation of the tangent line. That's awesome. Right here, what I did was I found the derivative, which I got over here, and I evaluated it when x was equal to 8, because I wanted the slope of the line when x was 8. This is the slope as a function of x. Once I tell you what x is, then you can find a definite number for this. All right, notation. We have our varied notation for derivatives. I've already gone over that. Let's look at example 3. We have a graph here. This graph apparently gives us the temperature that's measured in degrees Fahrenheit at given times of the day. Part A says estimate the rate of temperature at the following times for 1 through 4. Which of the following is the rate of temperature change at 7 a.m.? 6, 7, 8, 9. So it looks like the temperature at 7 a.m., here's 7 a.m., the question is, what is the rate of the temperature change? First of all, is this temperature change increasing or decreasing? It's increasing, so that means that the tangent line at that point is going to have a positive slope, so the derivative has to be Because the derivative's a rate of change, remember? That's why I'm talking about derivatives, by the way. Remember in the previous section when we had those 4 things in the box that said what a derivative means? One of them was a rate of change. This rate of change has got to be positive. So we can automatically cross out these negative choices. If we cross out the negative choices, that means we're down to 2. It's either going to be a small rate of change or a large rate of change. Which seems to make more sense? Does this slope appear to be 1 or does it appear to be 11? 1, I agree. Which of the following is the rate of temperature change at 9 a.m.? 9 a.m. is this point right here. Positive or negative? Big or little? It's still little. As a matter of fact, that tangent line looks to be about the same as slope as that. It's just slightly different. I'm going to go with this one. That's 11.6 degrees per hour. At 9 a.m., I don't think the temperature is changing that much. Which of the following is the rate of temperature change at 2 p.m.? 2 p.m. is right here. That tangent line is becoming more and more horizontal, isn't it? Okay, so is it still positive or negative? Is it going to be smaller or bigger? Smaller. It's getting closer and closer to 0. Horizontal lines have a 0 slope. And then part 4, which of the following is the rate of temperature change at 4 p.m.? 4 p.m. is right here. Is our temperature increasing or decreasing? Is it decreasing rapidly or not so rapidly? Negative 1.4. All right, part B. At what time does the temperature increase most rapidly and decrease most rapidly? We're looking for the steepest line with a positive slope. At what time does that appear to be? 10:30? That's about right there. So increasing, we're going to say about 8 a.m. All right, decreasing then. Where is it decreasing most rapidly? That's going to be the latest time of the day, isn't it? We're going to say 6 p.m. We're looking for the point at which the tangent line would have the most vertical slope. It's never completely vertical, but where it's the most vertical relative to the other times. And then part C, which of the following is the graph of the derivative of the temperature T versus time T? All right, one of the things you need to notice is this is increasing. You've already said that, right? If the function is increasing, is the derivative going to be positive or negative? Positive. The derivative is going to be positive. Right here at this time, the graph of the function has a horizontal tangent. What is the slope of a horizontal line? 0. And then when we start decreasing, right here, the slope is going to be. So I'm looking for a graph over here that goes from positive to negative, and it's equal to 0 about 9. So we go from positive to negative, and we're equal to 0 about, I didn't mean to pick the one that was actually it, but that's it. It does look like C. Do you see how we made that decision, though? This indicates it has a horizontal tangent early in the day. That's not the case. Once again, early in the day. This went from negative to positive, and this didn't do it. It went from positive to negative. The 0 is on the x-axis. This is a graph of the derivative compared to a graph of the function. Theorem 1, differentiability implies continuity. This is really nice. If a function f has a derivative at a point, then the function is continuous. Anytime you know that the derivative exists, the function has to be continuous. The other way is not true. Just because a function is continuous, it does not mean it's differentiable. This is called a conditional statement. If, then, only. If it's differentiable, then it's continuous. It works only one way. For example, here's a continuous function, and the derivative exists everywhere. Here's a continuous function, but the derivative doesn't exist right here. Because remember, a derivative is a limit. The left-hand limit is -1. The right-hand limit is +1. The left-hand limit is not equal to the right-hand limit, so here we say the derivative does not exist. Anytime you have a sharp corner like this, the derivative is going to be undefined. Example 4. At what domain points does the function appear to be differentiable? Is it differentiable only at x equals -1? Is it differentiable only at x equals 2? Is it differentiable between -1 and 0, not including 0, and between 0 and 2, not including 2? Or is it not differentiable anywhere? A, B, C, or D? If the function is differentiable, that means the left-hand limit's got to equal the right-hand limit, and that happens over this range. But right here at 0, we have a sharp corner or a cusp. The derivative will not exist right there. The derivative does not exist at x equals 0. Let's do this. F prime of x does not exist at x equals 0, but it exists everywhere else. At what domain points does the function appear to be continuous but not differentiable? I guess I kind of answered that before I read the question. When does a function not have a derivative? You need to know these. It does not have a derivative if you have a corner. This previous graph had a cusp. Or if you have a sharp corner. For example, you got a function going like this and then it goes smooth. That doesn't have a derivative at that point. If you have a cusp, the function does not have a derivative. If you have a vertical tangent, because remember the slope of a vertical line is undefined, so if your tangent is vertical, no derivative. Or at a point of discontinuity, because the left-hand limit won't be equal to the right-hand limit. So here's a couple of points of discontinuity where the limits don't exist. Either a removable discontinuity or a non-removable discontinuity, like right here. Questions? Yes.
But a limit still exists on that one, like it's moving towards.
The limit exists right here, but remember the derivative is more than just a limit. It's the slope of a tangent line. And if I want a tangent line at this point, it's going to end up being a vertical line.
Oh.
So the left-hand limit and the right-hand limit are the same, but we end up at that point having a vertical tangent. And that wraps up this section.